We left off looking at the exponential function and the log function. Now we're interested in, well, how can we perform calculus with it? We know how to do calculus with polynomials. What about this function? So differentiating the exponential function. Let's create a formula. We go back to first principles, the first idea of calculus. That means I need an expression for function x. There's my basic exponential, a to the power of x. So function x plus h, a to the power of x plus h. We put that into our first principles formula and see if we can't come up with something. Okay, limit as h approaches 0, a to the power of x plus h minus a to the power of x all over h. I could factorise the top of that. It's got a common factor of a to the power of x because of our index laws, of course. A to the power of x plus h means a to the power of x times a to the power of h. And a to the power of x, there is no h in that, so I could factorise that out of the limit. Really then what I'm interested in is this limit. As h approaches 0 of a to the power of h minus 1 over h, which if we were to do a direct substitution would give us that 0 on 0 problem. So let's look at that. I'm going to rewrite it. I could rewrite a to the power of h as a to the power of 0 plus h. And I could rewrite 1 as a to the power of 0. Seems a strange thing to do, but why do that? Because now I could rewrite the top of that fraction as function 0 plus h minus function 0. Remember, function x was a to the power of x. And when I look at that, I recognise what that is. That's, again, the first principles formula for differentiation, but not function dash x, but function dash 0. And what is function dash 0? Function dash 0 is the slope of the tangent. That's what we use to measure the slope of the tangent. So whatever the slope of the tangent is at the y-intercept, when x equals 0, that will be the answer to that limit. Alright, that gives us a sort of a formula we could use. If function x is a to the power of x, then f dash x will equal m, some number, times a to the power of x. And m will be whatever the slope of the tangent is at the y-intercept. Come back to that later. Now I'm going to introduce Euler's number, represented by the letter E. E for Euler, I guess. It's an irrational number. So just like pi, it'll go on forever and it will never repeat. That's its definition. The limit as n approaches infinity of 1 plus 1 on n all to the power of n. So if you substitute in bigger and bigger numbers, you'll get closer and closer to the value of E. A decimal approximation looks like it's repeating, but that's all to do, of course, with the limits of the size of the screen. And trust me, after 1828, 1828, it does go out of that pattern. It doesn't keep repeating like that. Now, what we do know is the exponential function, where the base is this wonderful number, Euler's number, it will have a slope of 1 at the y-intercept. So therefore, if function x is e to the power of x, remember we just said the derivative was m times e to the power of x, where m was the slope of the tangent at the y-intercept, which we've just said is 1, then the derivative is also e to the power of x. What this basically means, the slope of the basic exponential function, the one with the base of this wonderful number e, is always equal to the height of the curve above the x-axis, because the y value will always be the same as the derivative. And this explains why the exponential function rises so rapidly. So it starts very shallow because the y value is very small, but then as the y value is going up, well then it gets steeper, and then it gets a bit steeper because it's going up in line with the y value, and it'll get steeper and steeper and steeper and goes up really quick. Okay, some examples. Okay, this first example really is just, oh, do you know how to use your calculator? If you had to find e cubed, punch it on your calculator, you should get to 3 decimal places, 20.086. If you had to draw this sort of curve, we can still use all our basic curve sketching ideas we've seen. The basic curve here is e to the power of x. Okay, we'll draw that in. What have we done to it? Well, we know we've reflected it into the y-axis because we have function negative x. Let's flip it. There we go. What else have we done? Oh, but we've also reflected it in the x-axis because I also have negative function x. There we go, minus 1. In other words, we've performed a rotation of 180 degrees because we have negative function negative x. We got negatives on both the x value and the y value. There's our rotation. But there is one more thing we've done. We've also shifted it up 5 units. And so there is our final curve. That'd be where that one is. So to start off with, 11A, just the first 2 questions. And I've printed off in the notes there a picture of the graphs there to use for those ones. And then 11B as well.